How to size, calculate the purchase cost, and develop mechanical design for reactor by expert team B, DT19 and DT28.
So these are the team members from DT19, which are Nur Hakim Syed, Arif Hashri, Aurelia Salwa, Chui Yang, and Pang Sok Hui.
These are the members from expert team B, DT28, Loresh Patmanaban, myself, Megat Almin bin Megat Johari, Nurulani Shafika binti Muhammad Kanafi, Tanzi, and Tam Yuzwan. Hello everyone, today we are going to explore different types of reactors used in chemical engineering. Reactors are vessels designed to contain and control chemical reactions, and they are the key components in chemical engineering, influencing both the efficiency and output of the chemical process. There are three main types of reactors: batch reactor, double plug flow reactor (BFR), and bag mix reactor. These reactors are used in various industries, including pharmaceuticals, petrochemicals, and food processing. Moving on to reactor principles, the material balance for reactor is given by rate of accumulation of species I in the volume element is equals to rate of inward flow of species I into the volume element minus rate of outward flow of species I from the volume element plus rate of species I generation in the volume element. This is equation 13-1. Moving on to the next equation is the energy balance equation, which is expressed as rate of energy accumulation in the volume element is equals to rate of inward energy flow into the volume element minus rate of outward flow energy flow from the volume element plus rate of energy generation in the volume element. This is equation 13-2. Now let's discuss two important parameters in reactor design: space velocity and space time. This parameter helps determine the efficiency and capacity of a reactor. Space velocity and space-time. Space velocity, as we measure the volumetric flow rate of feet per unit volume of the reactor. Meanwhile, space-time tau means the time required for the reactants to pass through the reactor volume. This is the equation for space velocity. Space velocity is equals to Fi multiplied with VIF over VR is equals to Fi over VR multiplied with CIF, where Fi is the feed rate of component I, BIF the volume of the feed per mole of component I in the feed, and CIF the concentration of component I in the feed as mole of I per unit volume. And therefore, space-time is the inverse of space velocity. Moving on to the next slide, type of reactors. There are three types of reactors which we will be focusing on today. First one is batch reactor, a closed system where no reactants are added or products removed during the reaction. Second is the tubular plug flow reactor (PFR), a type of continuous reactor where reactants flow through a cylindrical tube in a plug manner with no back mixing. The third reactor is back mixing reactor, a type of continuous reactor where the contents are well mixed, resulting in a uniform composition throughout the reactor. Let's start with batch reactors. A batch reactor is a closed system where no reactants are added or products removed during the reaction. All reactants are loaded into the reactor at the beginning, and the reaction mixture is kept under specified conditions for a set time. No material is added or removed during the reaction, and products are removed after the reaction is complete. Batch reactors offers high flexibility and control over reaction conditions and have a simple design and operation. However, they also have disadvantages such as high labor and time cost, and also difficulty in maintaining consistent product quality for a larger scale operation. They are commonly used in pharmaceutical, fine chemical, and biochemical processes. Here we have the sketch of batch reactor and also the image of a actual batch reactor from the industry. Moving on to the next reactor, PFR. A tubular plug flow reactor is a type of continuous reactor where reactants flow through a cylindrical tube in a plug manner, meaning that there is no back mixing and each plug of reactants moves through the reactor experiencing the same conditions. In PFR, reactants enter at one end and flow through the reactor as a well-defined plug. Each plug of reactant experiences the same conditions along the length of the reactor, and the reaction rate varies due to the changing reactant concentration. The typical design includes a long, narrow tube that can be coiled to save space. The tubular plug flow reactor has several advantages. The first one is it provides high conversion rate due to lack of back mixing. Second one is it allows better temperature control along the reactor length. Finally, it is suitable for large scale continuous production. However, there are also disadvantages. The design is more complex compared to continuous stirred tank reactors (CSTRs). It is also difficult to clean and maintain. And finally, there can be significant pressure drop along the length of reactor. Typical application of PFR includes petrochemical processes, gas phase reactions, and polymerizations. Here we have the sketch of tubular plug flow reactor and also the actual image of the reactor from the industry. Now let's move on to the final reactor, which is the back mix reactor, also known as the continuous stirred tank reactor or CSTR. This type of reactor is widely used in continuous process where thorough mixing is required. In a CSTR, reactors are continuously fed to the reactor and products are continuously removed. A mechanical agitator and impeller ensures thorough mixing, so the reactor operates under steady state condition with a uniform reactant concentration throughout. The Siesta offers several advantages. The first one is it is easy to operate and maintain. The second one is it provides good temperature control due to uniform mixing. And finally, it is suitable for reaction requiring consistent reactant concentration. However, there are also disadvantages. It offers lower conversion per unit volume compared to PFR. It also requires a large reactor volume to achieve the same conversion as a PFR. Finally, it is not suitable for reactions with slow kinetics due to the dilution effect. Finally, common application of CSTRs includes homogeneous liquid phase reactions, fermentation processes, and finally, wastewater treatment. Here we have the sketch of CSTR and also the actual image of CSTR from the industry.
Non-ideality of reactor means that the reactor or reactor system is not perfect ideally. This is true because imperfect distribution of material and energy due to transport limitation of reactant pieces, reactor pieces, non-reactive pieces, and catalytic pieces. The imperfect mass transport can cause a reduced reaction rate, increase in undesired reactions, and fouling of the reactor system. While the inefficient energy transport can cause a change in thermal performance, a minor major catastrophic change in exothermic and autocatalytic reaction, and unforeseen reaction that can be harmful and dangerous. The limitation of mass and energy transfer can be divided into the larger scale transport and molecular level transport. The table showing the difference between these two transports. The largest scale transport is caused by mechanical design issue, which is poor measurement and inadequate thermal management, while molecular level transport is due to the issue in fluid solid system. The transport method observability, autonomy consideration, and impact on non-ideality is shown in this table for these two different transports. Execution time distribution is the paramount to the performance of reactor, particularly as it relates to the reactor flows and its effects on the reactor non-ideality. It is an essential tool in chemical engineering for understanding the mission and flow behavior within reactors. They provide insights into how real reactors deviate from ideal model. There are three key components, which is cumulative edge, external edge, and internal edge. In PPR, sections of catalytic bed may have variations in resistance to flow. Some sections might offer less resistance creating preferred pathway or channel through which the fluid can move more easily. molecule flowing through this channel experience shorter resistance time because they traverse the reactor more quickly compared to those that take longer path through the bed with a higher resistance. As the result of this variant pathway and resistance, there is a distribution of resistance time with the PPR. This means that the different fluid elements will spend different amount of time in the reactor, leading to a non-uniform distribution of age. In CSTR, source-dependent or dead zone basis. For source-dependent, it can reduce the effective machine and resistance time and lead to entropy reaction and low efficiency. While dead zone, it leads to inefficient use of reactor volume and affects the overall performance of reactor by causing uneven distribution of reactor and products. Reactor reactor is a type of temperature reactor where a portion of reactor effluent is recycled back to the reactor inlet. The diagram shows the schematic diagram of the reactor reactor and its recycle ratio. The recycle ratio can vary from 0 to infinity. As the recycle ratio increases, the reactor will shift from the flow to the mid-flow. And also, recycling provides a means to control the degree of bad emission by adjusting the recycle ratio. The advantages of recycle reactor are reduced time for desired conversion and flexibility in conversion rate, while for the disadvantages are high feed cost, high operating cost, increased volume requirement, and lower conversion. To have a good performance of reactor, this is achieved by optimization. There is some deadline for optimization. First, select appropriate reactor type and arrange multiple reactors to optimize production. Second is control the operating condition, for example, the temperature, pressure, and concentration. The goal of the optimization methods is to maximize the desired reaction relative to competent reaction through control of temperature, pressure, concentration, and reactor design.
Design of CSTR reactor. So in this section, the design of a CSTR reactor will be discussed. So for the operating parameter of CSTR, there's going to be four operating parameter of CSTR. First is the temperature. So temperature directly affects reaction rate, typically following the Arrhenius equation. So the higher temperature generally lead to the faster reaction rate. Then the second parameter is the pressure. Pressure can affect reaction equilibrium, reaction pathway, and the physical properties of the reactant and products. So the third one is the residence time, which is the average time a reactant molecule spends inside the reactor. So it directly affect the extent of reaction, which is the conversion achieved. So the final operating parameter is feed rate. So feed rate is the rate at which reactant are introduced into a reactor, affect residence time and conversion. So this is the drawing design of the reactor, which is we choose that CSTR. So the left one is the front view and the right one is the top view. Steering mechanism of CSTR. So this is the type of agitator. There are a lot of type of agitator, but this is a few kind of agitator that can be used in CSTR. So first helical agitator, then propeller agitator, turbine agitator, anchor agitator, and pedal agitator. Buffers in steering mechanism of the CSTR. So buffers is a vertical strips attached to the inner wall of the reactor. So buffers is functioning to prevent the formation of a vortex and improve the mixing efficiency in the reactor. Typically, four buffers are used with a width about 1/12 of the reactor diameter. Type of heat transfer in CSTR that normally used in industry. First is the jacketed, where a jacketed reactor has an external jacket that surrounds the reactor vessel. So the heat transfer fluid has been used, such as water, steam, or oil, is flows through the jacket to either heat or cool the reactor contents. Then next is the coil. So the coil are immersed within the reactor vessel. Heat transfer fluid circulate through this coil to transfer heat directly to form the reactor contents. Lastly is the internal coil. Internal coil are similar to the standard coil but specifically designed to be placed inside the reactor vessel. They often spiral or loop around the interior to maximize contact with the reactor content.
For the mechanical design, our example we take for the CSTR. So we need to consider the reaction kinetics. So the rate law depends on the reaction rate to the concentrations of reactant within the reactor. For the first example is 2A becomes B, so the reaction rate will be kCa to the power of 2 because the reactant of A has the coefficients of 2. For the second example, there are two reactants A and B, so the reaction rate will be kCa to the power of 2. For the desired conversion, it refers to the fraction of a species that react. The conversion can be calculated by this formula, which is the X equals to the number of mole of A reacted over the number of mole of A inlet to the reactor. And this also shows the conversion calculation in the complex system. When designing our reactor, we also need to consider for the safety requirement. The first one, we can have the pressure relief system. Our CSTR should be equipped with the PRV or rupture disc to prevent over pressurization. And second, for the temperature monitoring, we can have the alarm or the automatic shutdown system to prevent the overheating condition. The third one is the corrosion resistant. The material used in construction should be resist corrosion from the reactant, product, and any other substances present in the process. And fourth is the fire and explosion protection. This may include the fire detection sensor, fire extinguisher, or the inert gas system. To determine the reactor size and shape, we need to estimate the volume. So we can calculate the volume of the CSTR by using this formula, where V equals to Fn naught times X over negative Ra, where the Fn naught is the molar flow rate, X is the conversion, and the Ra is the rate of reaction of A. For the aspect ratio, it equals to the h over d, where the h is the height of the reactor vessel and d is the diameter of the reactor vessel. The step to calculate the aspect ratio is shown here. For the material selection, we need to consider for the corrosion resistance, where the corrosion rate equals to W over AT. W is the weight loss of the material due to corrosion, and A is the surface area exposed to the corrosion, and T is the explosion times can calculate in years. And for the corrosion allowance, it provides a margin of safety by ensuring that the remaining material thickness after corrosion does not compromise the structural integrity of the reaction vessel. The equation is equals to the corrosion rate times design life, where the corrosion allowance in mm or inch and corrosion rate in mm per year or inch per year and design life in years. Besides of the corrosion resistance, you also need to know the thermal conductivity. It is a material property that can quantify its ability to conduct heat. It represents the rate at which the heat is transferred through a material per unit thickness and per unit temperature gradient. So the Fourier law of heat conduction, the equation is Q equals to negative Ka times dt over dx, where the K is the thermal conductivity of the material and A is the cross-sectional area, and dt over dx is the temperature gradient. And for the thermal resistance, R equals to L over Ka, the L is the thickness of the material. And for the heat transfer rate, Q equals to Ka times delta T over L. The delta T is the temperature difference and the L is the thickness of the material.
Hi, my name is Nur Hakim Shahid, and I will explain about design of reactor in context of material construction and instrumentation and monitoring. Firstly, I would like to explain about material construction, which typically is industrial, which are stainless steel, glass-lined steel, alloys, and polymer materials. First is stainless steel, which is typical material construction used for reactor. It can withstand high pressure and temperature and can withstand corrosion. But the drawbacks are such as it may contaminate the reactant or product and only limited to certain chemicals. Next is glass-lined steel. This material mostly used for corrosive chemicals. Instead of using stainless steel, this material helps to prevent reactor from corroding. But since the reactor is made of glass, limited temperature can be applied to perform the reaction. Other than that, alloys can also be used to build the reactors, which may help certain chemicals to react without interruption. It also requires high maintenance, and due to its properties, it may highly cost to build one. Lastly, polymers may also be used in constructing reactors. It applies for chemicals reaction with low pressure and temperature. So, from all the materials construction given, choosing the best materials for building reactors is important to optimize the cost and maximize the product quality. Next, after designing reactors of materials construction, then we move into instrumentation and monitoring. There are 9 elements for instrumentation and monitoring. Temperature sensors are required in every reactors to determine the temperature of reaction occurs in reactor. There are two temperature sensors commonly used in industry, which are resistant temperature detectors (RTD) and thermocouples. This is the differences between RTDs and thermocouples. Make sure that we choose the best temperature sensors for our reactors so that it has the best cost and the best accuracy to detect our temperature in the reactor. Next is pressure sensors. There are three types of pressure sensors, which are piezoelectric, capacitive, and piezoresistive. Each of them has their own functions. This is the differences of the three sensors mentioned. So we must choose the best pressure sensors for our reactors according to the reactor's design. There are 6 types of level sensors typically used in industrial. The first three one is float switches, capacitive sensors, and also ultrasonic sensors. Next is radar sensors, hydrostatic sensors, and optical sensors. Each sensor has their own abilities and we must choose the best one for our reactors. Next is flow meters. There are 5 types of flow meters, which are positive displacement meter, turbine meter, differential pressure meter, ultrasonic flow meter, and electromagnetic flow meter. Next is pH sensor and agitation and mixing monitoring. It is advisable to put pH sensor if reaction occur required to maintain at certain pH. Agitation and mixing monitoring required to maintain the speed and power consumption of agitators or buffers. Lastly is data acquisition and control system. By gathering data from sensors, it will process and utilize the result to operate actuators and other components. Example is SCADA that has been widely used in industry to gather data from sensors.
So now we will discuss the costing of a reactor. In this section, the method of estimating the cost of reactor will be discussed. To estimate the cost of reactor, we have to follow 6 steps. First is we have to determine the design pressure, followed by wall thickness, followed by vessel weight. Next, we will estimate the purchase cost of empty reactor vessel. Next, we will estimate the cost of the platforms and ladders. And finally, we will determine the FOB purchase cost of the reactor. Now, we will go through an example together. The example is taken from Seder book, page 467, example 16.12. An adiabatic reactor consists of a cylindrical vessel with elliptical head, with an inside diameter of 6.5 feet and a tangent to tangent length of 40 feet. Gas enter the reactor at a pressure of 484 psia and 800 Fahrenheit. Exit conditions are 482 psi and 850 Fahrenheit. The vessel will be orientated in a horizontal position. Estimate the vessel thickness in inches, weight in pounds, and purchase cost in dollars for a CE cost index of 600. The vessel contains no internals and the gas is non-corrosive. The barometric pressure at the plant site is 14 psi. We will start with calculating the design pressure (PD). For the operating pressure from 0 to 5 psig, the design pressure will be 10 psig. For the operating pressure from 10 to 1000 psig, the design pressure can be calculated using equation below, which is equation 16.61. For the operating pressure more than 1000 psig, the design pressure will be 1.1 times operating pressure. Since our operating pressure is 470 psig, we will use the equation to calculate the design pressure, which is the answer is 546 psig. Next, we'll continue with calculating wall thickness Tp. The wall thickness can be calculated using equation 16.63, where the Tp is wall thickness in inches to withstand the internal pressure. Pd is the internal design gauge pressure, which we calculated before. Di is the inside shell diameter in inch. S is the maximum allowable stress of the shell material at the design temperature in pound per square inch. E is the fractional build efficiency. From the question, the higher operating temperature is 850 Fahrenheit. We have to plus 50, then the design temperature is 900 Fahrenheit. A suitable material is low alloy steel. So from the table in book schedule 466, the maximum allowable stress is 13,100 psi. We assume that the wall thickness will be greater than 1.25 inch, giving the work efficiency E of 1.0. Hence, the wall thickness will be 1.667 inches. Next, we'll continue by calculating the vessel weight W. W can be calculated by using equation 16.59, where L accounts for the cylinder, the terms in 0.8 di accounts for the tool head, and rho is the density of the carbon steel. Because the orientation of the vessel is horizontal, the vessel is not subject to wind load or earthquake considerations. Adding a corrosion allowance of 1 over 8 inch gives a total thickness of 1.792 inch. Since this is in the range of 5 over 8 to 2 inch, the steel plate comes in increment of 1 over 8 inch. Since 1.792 inch is greater than 16 over 8 inch, we will specify a plate thickness Ts of 17 over 8 inch or 1.875 inch. Hence, the vessel weight is 72,500 pounds. Next, we'll continue to estimating the cost of empty reactor vessel (CV). For horizontal vessel of weight from 1,000 to 920,000 pounds, we can use equation below to estimate the cost of empty vessel, which includes the nozzles, manholes, support, based on the weight in pounds of the shell and the tool head. Hence, the purchase cost of the vessel in question is given by equation 16.53, which CV equals to $99,700. Next, we'll continue with estimation of cost of platform and ladders (CPL). For horizontal vessel with DI from 3 to 12 feet, the added cost (CPL) for platform and ladders depend on the vessel inside diameter (DI) in feet, which is given by equation below. equation 16.55. From table 16.26 in Brookseder, page 467, the material factor is 1.0. Thus, Fm times Cv equals to $119,600. Hence, this is added to the cost of the platform and ladders from equation 16.55, where CPL equals to $5,660. Finally, we have to achieve the ultimate goal of estimation of FOB purchase cost, CP. The FOB purchase cost, which is for carbon steel construction and includes an allowance for platforms, ladders, and a nominal number of nozzles and manholes, is given by equation 16.52. Using the equation, the purchase cost at a CE index of 600 is given by CP equals to $132,500.
This is the Excel working instructions. As for the first step, user is required to input the related information as shown in the figure below. This calculator restriction is that it is only suitable for the adiabatic reactor consisting horizontal cylindrical vessels and the vessel contains no internals and the gas is non-corrosive only. Second, after keying the data, the calculation will be done in the costing sheet. However, the user should read the instructions below to proceed with the calculation. After inputting the data, there will be two conditions that requires the user to manually input the data. As shown in the tick box there, either A or B will appear in that box, which related to condition 1 and condition 2 respectively. The following data will be automatically calculated in Excel. In the condition 1 where A appears, user has to manually input the TP selected in the yellow box based on the vessel inside diameter DI. This is because the TP calculated is less than 1.25 inch based on the user input data. So, the user now should input the minimum wall thickness based on the vessel inside diameter key in the yellow box. In the same condition, after TP has been selected, the user should proceed to manually input the TS black thickness in the green box, where user has to refer to the diagram below. Condition 2, where B appears, user should directly go to the costing sheet without bothering the TP and to manually input the TS according to the TP calculated. After the user has input the TP or TP is automatically calculated, TV will be then calculated, which is the total calculated thickness. So in the example, the total calculated thickness TV is 1.79 inch. Thus, by referring to the nominal size of steel plate, the actual plate thickness TS should be 1.875 inch. The vessel weight W is then calculated automatically, as well as the CV, CPL, and CP that the user desires to know.
So for the next part is reactor sizing, where in this part, the method of estimating a reactor will be discussed. So for the next part is the formula involved in sizing. First is flow rate estimation. By using conversion and selectivity, the flow rates are to be calculated first. Next is the equilibrium constant K. So this is the formula that is used based on temperature profile. The equilibrium constant or K can be found from using the temperature dependent K formula. Next is rate constant or small k. Rate constant value can be calculated by using Arrhenius equation. And lastly, the design equation for specific reactor. So for each and every reactor, they have different design equations. So for batch reactor, CSTR, PFR, and PBR, each of them has different algebraic form or integral form of design equation.
Here are the example of sizing that we can use to understand better. From the question given or example given, we need to extract data first, and we got see that 100,000 ton metric of styrene, and we assume that uh, 8,000 operating hours, and we must know that 97% selectivity for styrene, 88% recovery and recycle of ethyl benzene, and 70% conversion per pass-through reactor. So the first step that we can solve this problem is to extract data and find the design production rate. From the extraction data before, we can find the production rate, and we got 3.472 kg styrene per second. And from that value, we can find the fresh feed rate that we consider at 97% of styrene, and we got the value is 3.723 kg ethyl benzene per second. From the value before at step 2, we can find the feed rate of ethyl benzene at step 3, that we know that 70% conversion of per true reactor, and we got the value 0.05017 kg mole per second. And also we need to find the equilibrium constant K reaction 1 K1 to get the value to get the rate constant for reaction 1 later on. So for the step 5, we need to use the information from step 4, and we got the value rate constant K 3.23 times 10 to the negative 4. And from the equation, we need to change it to the mole fraction and must be expressed in terms of conversion. The formula that we use, we need to rearrange the formula in expressed in terms of conversion. So all the value we got, and we can find the reactor volume, and we got the value for volume VR is 17.24 meters square, and this is the example of sizing of reactor in our case.
For the actual calculation for sizing, the first step is to input the information you have, such as temperature, pressure, conversion rate, mole fraction, production, operation time, etc. on the green box. Then it will calculate the production rate, fresh feed rate, and required feed. For the equilibrium constant or K for the reaction, there is no specific formula as it depends on the reaction. Each has their own formula, so this step would differ for each reaction. But for the K for component, you can input delta H and KI value on the green box. The same for the rate constant, you can input the E and KI value obtained from literature on the green box. For rate of reaction, there are a general equation, but most of the time it is either given or have a different formula. You can input immediately if given or use the formula. And at the end, it would calculate the volume of the reactor needed for the reaction. The box that have a thick border is the output for each section. If you have a different unit, don't forget to convert the unit. That's all from me. Thank you.